Continuing on here from the workshop, we are in the sequential function chart discussions. We've completed two. As I said, it's one great big long discussion that in the classroom took a couple of hours and a number of breaks. So we've broken this up into 4 sections and they're still long. So let's continue on and do part 3 of sequential function charts. Welcome back. This is part 3 of sequential function charts. Before we leave this piece of sequential function chart, sequence the sequential function chart between the start and whatever you named your step there. I called it A step 001. Each time toggling input 1 on and off. Ponder this for a moment. What can you say about the stored qualifier to sum up everything that you've observed so far? Now you probably wrote something like, the stored qualifier stores the activation of the action and the action continues to execute until you reset it or stop it by some other means outside of the step. Whereas the non-stored only executes while the step is active. Now, if you were going to do this with program control, you would have a JSR in your main program or whatever. And you know, I've mentioned in the past many times that with ladder logic diagram, ladder 2 is the only file that executes automatically when you go in the run mode. If you want to execute ladder 3 through whatever, you have to use a JSR to get. The only exception to that, and it's really the same thing, you still have to JSR out of ladder 2 to some other ladder routine, and then you can JSR from them. You can go like 7 layers deep with 500. I'm not sure with 5000. Typically, I don't do spaghetti code. In other words, I don't create a real convoluted program control. But in the routine where you have all your JSRs, you can put a permissive, a condition on that JSR that when you make the condition go true to execute JSR to that routine, you can then latch it on and you don't have to come back and repeat the condition. In other words, you can use it like sealed in logic for a start-stop push button arrangement on a motor starter. You start it and it stays until you hit stop. That's how you would do a stored. So stored, sealed in, and you can do this with regular program control in ladder 500. With RSLogix 500. You just have to use the conventional start-stop logic that you would use with a push button to run a motor, only use it on your JSR. Now we're going to change this to a time limited. So we go to Edit, drop down the list, pick L, finalize all edits, get rid of this message, we don't need it. That won't let us delete this message until, okay, 0 errors, 0 warnings. That's what we expected. Now let's run this. Now this is time limited. I had to do a very specific sequence in the lab book. Save changes. If offline, then download. If online, then finalize all edits. And let's characterize the L qualifier. Characterize might be a term you're not familiar with. When you characterize something, you throw everything at it you can think of and let it identify its character. With humans, if you wanted to characterize someone, you would put them under a lot of stress. For instance, when I was in the Marine Corps, they would characterize you by exercising all means of what you would call creative profanity, including about your family members, to see if they could get you to lose it. I mean, the goal was to push you until you broke, to characterize you. When you characterize something, and we do that a lot with our programming. As we write a program and we kind of push some things to the limit and we kind of find the edge. If you go beyond that edge, you get unstable behavior. So you kind of characterize it. So that's what we're doing now. We're characterizing these qualifiers. Toggle N1 on and off observing output 1. Was there any reaction? Well, of course not, because start 1 is active, step 1 is not active. While watching the state of your second step, press and release input 0. See, you see what happened? Well, let's do that again. Go back to start. Now watch the step and the action. When I press input 0, step 1 goes active, the action goes, oh, bang, it disappeared after 2 seconds. Now I had 3 seconds in the lab. So I'm going to lengthen that up, and I'm going to pause to do that because it disappears too fast. As you can see, I've changed the preset to 3000 milliseconds. We'll do that again. We have to go back to start, and then we'll transition into step 1. You see they both go active, and after 3 seconds, the action deactivates. It's time limited. Then I had you press and release input 1 repeatedly. Okay, well, nothing's happening. I'm doing it. Nothing's happening. Why? Because that action is now not active. The step is active, but the action is not. Okay, press and release input 2. This sequences the SFC back to the start step. Now get ready for some fast action. You're going to press release input 0, then quickly start press and releasing input 1 repeatedly. Okay, we're going to do that. Goes active. I'm pushing, it's going on and off. Oh, the action deactivated and the light's still on, which means that I had my finger on input 1 pushing it down when that 3 seconds ran out, and the last thing it did was it says turn on local 1 0 data 0. If I had just been a little bit quicker at letting off with my finger, then it would have turned the light off. Press and release input 2. Take a breath and repeat this previous step. Did you get the identical result? Nope, this time when the 3 seconds ran out, input 0 was off. So it just depends on what the program is doing, this code. Remember that input 1, that's your finger. You're running this on and off right here, this tag. So it just depends on whether or not the tag is on or off when the 3 seconds runs out. So we have characterized the L qualifier. And in the lab I said summarize the behavior of code that is in the L time limited qualified action. As long as the action is active, the entirety of the code is being executed. If the code can produce more than one result, meaning states, then whatever state was there when the 3 seconds or the time limit was up, it leaves it exactly like that. Now we'll do that one more time simply because I want to leave that, make sure that that light is in the off condition. So go 0, the light is off, I'll just let it time out. Now the next thing we're going to do is we're going to do a time delayed qualifier. So I'm going to pause, edit the code, and then come back. Making sure that you have toggled the program out of the run mode and back into the run mode, in other words to program and back, that you have not sequenced out of the start step since the mode change. Prepare for fast action once again. Toggle input 1 repeatedly while watching output 0. Now we're still in the start, so if we toggle input 1 repeatedly, we shouldn't see anything. You know, output 0 is not going on and off as we toggle the push button. Toggle input 0 and then begin toggling input 1 repeatedly for at least 4 seconds. It has to be for longer than the preset on that time delayed qualifier. So we push input 0, then we start pushing input 1 repeatedly. Toggle input 0 and then begin toggling input 1 repeatedly for at least 4 seconds. What happened in detail? We went into step 1, we started pushing the button, nothing happened. And at the end of 3 seconds, the output 0 started flashing on and off as we pressed and released input 1. Toggle input 2. Notice that when I toggled input 2, this is not stored. This is non-stored. It's time delayed and it's non-stored because as you can see, the action is no longer active. Any reaction from output 0. We toggled input 2 and then 1. Nothing happens because it's not a stored action. Repeat the previous 2 steps with the start step active, but to hold down input 1 after output 0 starts responding. So as we go into step 1, and then we start toggling the button, but we hold it down until 3 seconds runs out, then we push input 2. What happened? Well, the light stayed on, didn't it? Because we are no longer active, that's not a stored action. So again, even though you time delay, you just delay that action. So if you transition into step 1 for 2 seconds and then transitioned out of step 1 back to the start, that code never got executed, because remember, the timer has a preset of 3 seconds. If I go into step 1 and then go into step 2, see, it never went active because it's time delayed. Which of the earlier qualifiers does this behavior bring to mind? Which of the earlier qualifiers does this bring to mind? Non-stored. If we go into step 1, after 3 seconds, delayed by 3 seconds, the action goes active, and it stays active until you leave step 1. If you're going to rename this qualifier to make the name more implicit, how would you rename it? I would call it TimeDelayed non-stored. To summarize the behavior of this qualifier, since the action is delayed for 3 seconds after the step goes active, which we'll repeat that, watch closely, going to activate step 1, and then 3 seconds later, the action goes active. So during that 3 seconds, if you were to step on through step 1 to the next step or out of step 1, during that first 3 seconds, then the code was never executed. So we'll go back to the start. I'm going to go to step 1, and then I'm going to leave step 1 before the delay was finished. That's how you would use the delayed time or time delayed action. Now we're going to do another qualifier. We're actually going to have a time limited and a time delay. We'll have both actions in one step. This is the next step in your lab book. We had you take the existing sequential function chart, or we gave you the choice of creating a new routine, and then you can always copy the sequential function chart from the old routine, paste it into the new, and then make the modifications. In this case, I've been just modifying the same sequential function chart. So you can see that we changed the action from whatever it was. We changed it from a time delayed to a time limited. Then we added another action that was time delayed. The time limited, we set a preset of 3 seconds, and then for the time delayed, 2 seconds. The code or the structured text is identical with the exception of the object of the structured text, which is, in this case, output 0, and this is output 1. This time, after turning off all the switches and toggling the mode to the program mode and back, after you have toggled the mode run to program back to run, you are going to toggle input 0, and that's going to shift the sequence into step 1, a step 1, and then immediately start toggling input 1 repeatedly for 5 seconds. Now you don't have to do it real rapidly, just on, off, while watching output 0 and output 1. Before you toggle input 2 to transition back to the start step, make sure that you are holding down input 1 when pressing input 2. Think this through before you start. So once more through that sequence. We press input 0. That activates step 1. But it is time limited. You have to act almost immediately so you can see the behavior of the time limited action. And you're going to continue toggling input 1, which is used in both actions, for at least 5 seconds. You go all the way through the time limited and you make it into time delayed, and then you're going to hold down input 1. I mean, you can let go of input 1, but before you press input 2 to transition out of step 1, you need to hold down input 1 so the last execution of the time delayed action is with input 1 activated, energized, or on. Now go ahead and toggle input 0 on, then input 1 repeatedly for more than 5 seconds. I'm toggling it now. Okay, and I've not toggled out of that step. You see it's still active, and here's what I saw, and here's what you probably or should have seen as well. When you were toggling input 1, at first, input 0 was the only one that came on and off with the push button. Then after 3 seconds, both inputs were toggling on and off with a switch, but at the end of 3 seconds, only input 1 was toggling on and off. And you see that the time delayed action is still active. So you can still toggle output 1 on and off with input 1. What you should have observed is this. When step 1 went active, the time limited action also went active. And as you toggled input 1, you should have seen output 0 go on and off with the push button. After 3 seconds, then you would see both output 0 and output 1 toggling off with the push button. Then after 1 more second, because there's an overlap, the time limited is 3 seconds, the time delayed is 2 seconds. So for the first 2 seconds, all that you see going on and off is output 0. And then for 1 second, you see both lights going on and off. And then after 3 seconds total, the first action has timed out, and all that you're left with is the time delayed. And of course, that stays active as long as the step is active. If we press input 2, which I'm going to do now, I'm going to hold down input 1, as I said to do, and both lights are on, and then I'm going to push input 2, and see we toggle back to the start. I let go of the button, and both lights are on. Now the reason both lights are on is because when the time limited action timed out, I happen to have the push button pressed. Output 0 was on. It stayed on. It's still on right now. And then, of course, I held down input 1 so that output 1 would also be on. So both lights would be on. And then I pushed input 2, toggle back to the start. Let's modify this sequential function chart again. Only this time we're going to eliminate the actions and then add an action that is non-stored, and we're going to do a JSR to a ladder file. Okay, we've eliminated the 2 actions. We have an action that is a non-stored qualifier. We're going to double click in here, and I'm going to do a JSR. Open parentheses, and I'm going to right click inside, browse routines. You could have just typed it in, and we'll pick ladder logic diagram 4. It really does not matter what ladder logic diagram you pick. It could be a simple routine that has 1 rung in it with a push button and a light. We just want to demonstrate using the JSR. And then we need a close parentheses and a semicolon. And that's all we need to use an action. Non-stored means that it's only going to execute that JSR when you're in step 1. Of course, you could use a stored, and the first time you go to step 1, it's going to jump to that subroutine, and it's going to keep running that subroutine until you do a reset later on in your sequential function chart. So we'll finalize all the edits. Zero errors, 0 warnings, that's what we want to see. Let's open up ladder logic diagram 4 so you can see what's in there. And I'm going to jump back to sequential function chart 2, and I'm going to toggle input 0, and it's as long as we're in step 1, this is non-stored, but as long as we're in step 1, this is going to be active. So now we can go to ladder logic diagram 4, and I can push input 0. Now the only fly in the ointment, as they say, is that if I was using input 2 here, which I am, the reset push button, When I push that button, remember we're executing the SFC too as well. So you need to be careful what you're doing with your I/O or your tags, that you don't use the same tag for two different things. In this case I did, but I'm not going to worry about it. I'm going to push input 0. You see that the timer's timed out and the latched LED is on. I'm going to push input 2 now. We'll see if it unlatches that before it actually transitions out. So I'm going to go back to SFC2. I can see my light on. I'm going to push input 2. That transitions back to start, but the light is still on, which means that it transitioned out of step 1 before it executed that action. So it did not read this wrong and unlatch that bit. Now, if I wanted to fix this, I would probably go back to Sequential Function Chart 2. I would put it in the edit mode, and I would use a different push button, finalize all edits. Now we'll go into step 1, and I will push, let's go to ladder logic diagram 4. I'm going to push input 2 to reset, then input 0. Now if I wanted to display the start LED and the timer timing LED, remember I have to flip on switch 1. Now when I press input 0, the first 2 lights come on for 1 second, and then as long as I'm holding down the button, the timer is still enabled. So I have the start LED and the latched LED on. I let go, the timer resets, and if I push input 2, so this logic is working fine, and we're still in sequential function chart in step 1. So if I press input 3, toggles us back to start. Well, we went over the basic qualifiers. There are more qualifiers that we could talk about. We're going to save that for a more advanced section on sequential function charts, probably volume 3. Next, we're going to do branching. And branching, of course, is just like branching in ladder logic. Branching in ladder logic is always an OR, logical OR situation. That's not necessarily true in sequential function charts. There are 2 types of branches. There is selection branching, where each branch has a transition at the head of it, and you can only select one of those branches, or I guess I should say, whatever transitions you make true, those are the branches that are executed. Whereas simultaneous branching, there are no transitions. You transition out of the step into the simultaneous branch. You can do this online or offline, create a new routine, or modify an existing, your choice. Offline is always the simplest and fastest for this level of editing. So retrieve or recreate the sequential function charts that you saw in the lab, and you're going to use a stored qualifier. In the lab, I created new tags for the transitions because I wanted to show a more organized sequence of numbers. So first let's save, and I'm going to pause. And now that we've saved, we can go offline. And I'm going to edit some of these tags. One thing I didn't show you, I might as well show you right now, and I believe I can do it in Tools, Options, Sequential Function Chart, Element Naming, Create Tag with Language Element. I turned that off. That was turned on. You have a whole array of things that you can set here to give you the base name. This was turned on, Generate Tag Name. It was called Step Transition Action, or we didn't do any stops. And then the second part of it was underscore and then a sequential number. I'm going to turn this off because I do not want to automatically generate tag names as I add new elements. I would just as soon name my own. So I want this to be start, and I'm offline, so I can just double click start. Now these tags already exist. Remember, these tags were created earlier on in the sequential function charts, and we're going to make this transition 100. If that tag did not already exist, we would have gotten a red X to show that this was an unhappy transition. We're going to make this step 100. And we'll make this action 101. This will be transition 200. So these tags already exist. So now we have start transition 100 goes into step 100. And in step 100 we have action 101, 102, etc. And then transition 200 theoretically would transition into step 200. Now you can name these steps and transitions and actions with almost anything you want. The same criteria for tag names applies also to the names of these elements because they are tags, but they are of a data type, sequential functions chart step. This tag is a Boolean and it's a single bit, whereas the tag for start or for step 100, these are actually a specific data type. Sequential function chart step is a data type. We could do an aside here real quick, I guess. Go to predefined and then scroll down to sequential function chart step. And here are all of the elements, all the members of the class of objects, sequential function chart step. We have a double integer, which is the status, and then we have a series of Boolean to show the condition or the state of that step. So we'll cancel that now that you understand. And of course this tag is just a Boolean. It's just a single bit. It's used similar to the way a one-shot is used. Each one-shot instruction has a bit in memory that represents the status of that one-shot. Has it been executed once on the run condition true or not? So now we've edited most of this. We want to change this to stored. Next we're going to eliminate this line. We'll add this line back in later after we've completed adding the rest of the elements. So select it, right click, delete wire. Now I know we just changed this to transition 200, but for right now we're going to delete this transition. We don't need it right this minute. So coming out of step 100, we want to select one or two paths. So we put the focus on this step, and then we go up and we select a selection branch diverge. Not a simultaneous branch diverge, but a selection branch diverge. Notice the difference. The simultaneous branch diverge comes with two steps. The selection branch diverge comes with two transitions. So we click, it drops down, and now let's start editing. You've observed already editing transition names and adding tags for the permissive for the transition, so I just quick bumped those in while you weren't looking. The reason that we did a selection branching is because we wanted to choose between two paths. So we need two transitions. Either one will transition you out of step 100. The transitions then obviously go to steps. So there should be a step beneath transition 200 and another step beneath transition 300. It's simply a matter of putting the focus on a transition and selecting step, or since we know we'll need a transition out, we could put our focus here and then select a step and a transition and do the same thing here. Now I realize I didn't do it that way in the lab manual. In the lab manual I had you do one element at a time. But to enrich the lab experience, I took a slightly different route. We will still end up with the same structure. Now let's name the steps and name the transitions and add the permissives on the transitions. Okay, now we've named everything. You may or may not have noticed this was 4 and 5 instead of 2 and 3. So I also changed that while I was out of your sight. So now that we've added our transitions and our steps, we need to add some actions to step 200 and step 300 to give the step something to do. So right click, add action, NonStored is the default. Let me scroll up here a little bit, and we'll call it action 201. And for an action, we want an output. So we browse tags, open up the box a little bit, type in LO for local, drop down. We want local 1, O for output data, and we'll use 4. Now you see we have a little problem here with overlap. So let's drag, and I probably should have, in the lab I think I had you drag this over before we added this step. So we'll see what we can get away with here. That looks much better. Now something's still not happy here. That's a good tag. That's a good tag, so it has to be our script. And of course we know that after any kind of expression, we have an output, but we're not telling it what to do. We want to make it equal to 1. See, now everybody's happy. Now we've got more overlap, so let's stretch it out again. Let's add an action to step 300, and we'll make it a reset. And we'll name it action 101. Actually, we're not going to name it action 101. We're going to reset action 101 up here. So we double click, drop down, and now we're looking for action 101 right there. See, now everybody's happy. We want to add another action, non-stored, and we'll call that action 302. Evidently that tag was already created, and for that action we want this structure right here. Control C, double click, Control V, and change that to a 0. Okay, now we want to bring these two branches back together, and it's just as simple as it was to add this selection branch. We want to now converge. Now you notice that this converge sequential function chart elements button is grayed out. If we select one transition, it's still grayed out. If we hold down the shift key and select another, you see now it's active. So we click on that, that joins them back together. That only leaves us one thing left to do, and for that we're going to have to geyser down so we can see the whole thing. We're going to attach a line from here down to here. Now it really doesn't matter where you put it. As long as it turns green, you let go, and there you have your completed sequential function chart. One thing that we really should always check when we've done that much editing is we should right click on the step that you want to be the initial step. In this case we want start to be the initial step, and make sure that initial step is selected. We're offline, so let's save and then download. Now I can just click on download simply because there is only one processor out there that this could go to. But just to be a good example, I will select the processor that I know is the one that I want and click download. Honestly, you should read this often enough to know what it says, because there are some particular, like here it says the controller is in the remote run mode. Now if it wasn't in the remote run mode, we could prove that by backing up and doing this over with it in the remote program mode, but we won't. Also, if you have some motion involved in your machinery and you go from the run mode to program mode so you can download, you may cause some unexpected motion. Now that should not happen if you have selected the appropriate components for your actuators. If it's pneumatic, then you should have blocking valves or some other arrangement, so when you go into the program mode you don't cause motion. So we click download. We see the progress. Done downloading. Change controller back to the remote run mode. Yes. And here we are running. 0 errors, 3 warnings. We don't care about the warnings. They're in other routines. And here's our sequential function chart. We can't see the whole thing, so I'm going to geyser down a little bit more so we can see the whole thing. Now remember, the only thing that there is to really see is what is active. So you can see the green highlight on the start. Also, we want to check to make sure that SFC02 is what's active. Close our predefined, and we'll go back up to the main routine, and we see that SFC02 is active right now. We could close these other 2 routines. We're not using them. If you can read that, as a matter of fact, I will, I guess, geyser up a little bit. And then we can always scroll down. That way it's easy to see. So you see input 0 is the transition. So we push the push button associated with bit 0 of that module. That transitions us into step 100. Now this is a stored action. If I toggle input 1, the light goes on and off. And if I have the push button pushed down when I transition out to the next step, the light will be on, but when I let go of the button, it won't stay on because this is a stored action. It's going to continue to execute long after we've left step 100. So the first time through, I think we'll transition 200 into step 200. And that requires that we do the next push button. So I'm holding down both push buttons. 1, now I'm going to press 2, let go of the push buttons, and now we've turned on output 4. When I let go of input 1, after I pushed input 2, the light that was turned on in action 101 up in step 100, that went back out. And you see that action 101 is still active. So right now, how many steps do we have active and how many actions do we have active? We have 1 step active and 2 actions. In the manual, it asks with step 100 or whatever you named it active, toggle input 1 repeatedly, observing output 0. I didn't ask you to do that, but you can still do that because it's still active. So the first time through, I had you toggle transition 200 into step 200. And again, I ask, how many steps are now active? Well, there's only 1 step active. Why? Well, because we transitioned out of step 100 into step 200, and transition 200 is one of 2 transitions in a selection branch. If this were a simultaneous branch, it's possible that 200 and 300 are both active simultaneously. However, keep in mind if it was simultaneous and one was time limited and the other was time delayed, you could have a situation where they're not both active at the same time, even though it's a simultaneous branch. I had you toggle input 1 repeatedly while observing output 0. And of course what happens is the lights goes on and off. That's because action 101 is still active. Toggle the condition for transition 201. We can see everything of importance. How many steps are now active? 1. Why? Well, only 1 step active at a time. In a selection branch, I suppose you could hold down inputs 2 and 3. However, because of the way this executes, is if you push down 3 and 2 together, 2 and 3 together, one of them's going to close before the other. And whichever one closes a split second before the other, it's going to go into that branch. It's not going to execute the other branch. So in this particular sequential function chart, only 1 step can be active at a time. Now, how many actions are active? Well, 2. One's stored, one's non-stored, but it's in an active step. Repeatedly toggle input 1 while observing output 0. What happens? Well, the light toggles on and off. Why? Because action 101 is still active. Toggle the condition for transition 201, which would be input 4, and we're back to the start. Toggle the condition for transition 100 to go back into step 100. There's no change in behavior simply because that action was already active, and now the step is active, but that did not change the state of the action because it is stored. This time around, while keeping one eye on output 4, and the other on the state of step 100 and the action, we're going to transition into step 300 by pushing input 3. So watch action 101 and watch your light that should be on now, output 4. Action 101 deactivated. We are now in a non-stored action 302, and its action is to turn off output 4. We execute transition 301 by pushing input 5. We're back to start. There are a few obvious questions in the manual. When did step 100 deactivate? Or rather, why did step 100 deactivate when we activated step 300? Step 100 deactivated because we transitioned out of step 100. Another question would be, why did action 101 deactivate when we activated step 300? Step 300 has a reset, and it resets action 101. Why did output 4 de-energize when we activated step 300? Because the non-stored action in step 300 is to turn off output 4. In step 200, we energized output 4 and it remained on until we activated step 300. What ladder logic diagram instructions does this behavior imitate, simulate, duplicate? I would say latch and unlatch, also called by some manufacturers set and reset. In ladder logic diagram, the OTE, output energize instruction, has a true and a false execution. In this case, we don't have any true or false instructions. We don't have a construct of if then else. We just have local 1 0 or local 1 0 for output, data 4 set it to 1, and then the other action 302 is set it to 0. So this looks like latch and unlatch. Another question, could you duplicate this program control with ladder logic diagram control of routines? Yes, you could. It would be fairly convoluted code, not easy to follow, but you could do it. Now what we're going to do, we're going to go back to offline. Actually, we don't have to go offline. So whether you did this online or offline, it really doesn't matter. In the lab, I have completely different transition and step names that you see in front of you. As a matter of fact, I think I'll just go change them to match. That will reduce any confusion between step and transition names, what in the screen in front of you and what you saw in the manual. Be right back. I've renamed some tag names. I've deleted a few things. Now I'll demonstrate adding a simultaneous branch, diverge. Select the transition. This is the transition out of step 1. This is the transition out of step 1 into the simultaneous branch diverge. So I click on that, and now I have the diverge and the 2 steps. So I'm going to pause a minute and edit this to add the tag names and the actions. Now we have our diverge, our simultaneous diverge. You notice that the transition transitions into both steps. To these 2 steps, we need transitions out of these steps. However, there are not transitions out of these steps because these are simultaneous. If we had transitions on each of these steps, then how could one step transition out to the next step while this one was still active? That wouldn't work. So we click on both of them. We bring the focus on both. Then we select converge. And now we can connect our remaining code that we had before. And I did change the tag names, so they should match fairly close to what is in the manual. So let's download this. And of course, I'm not going to make you sit here and wait for this to download. So I'm going to pause and then come back when it's downloaded. We're back to our favorite message, download. Pause again. Okay, here we go. We're online, downloaded, and we're running our code here. I see I already bumped it into step 1, which is fine. I'll quick run it through. I'm going to hit transition 2. Notice that both steps go active simultaneously. When I look over at my demo, I see output 4 and 5 on, but 4 is flickering. So that would be the unexpected behavior that you saw. The unexpected behavior you see is with 4. Sequence through until step 5. How many steps are active? Well, 2 steps are active until you cycle into step 5. So if we cycle into step 5 by pressing input 3, now how many steps are active? Well, 1 step active, 1 action. Action 5 is active. Steps 6 and 7 are active. Notice that if you look at your demo, that is if you have one, output 4 is flickering and output 5 is on solid. That would be some unexpected behavior. Why is that output flickering? It's flickering because you are simultaneously turning on and off output 4. So action 8 and action 9 are basically opposing each other. So output 4 is flickering on and off. To me, that's unexpected behavior. I would have thought last man wins if I was thinking ladder logic. So this is something to make note of. In action 8, non-stored, you're turning on output 4. In step 7 or action 9, you're turning off 4. When I look at 4, I can see it flickering on and off. Now, of course, we don't want it to do that. A real application, I don't think you would have any kind of actions that desired that kind of behavior. So how would you change the code to eliminate that problem? Since this is just some actions that we're playing with to demonstrate simultaneous branching, I would probably change this to turn on 5. So this turns on 4, turns on 5, or this turns off 4 and on 5, and then have this be opposite down here. It really doesn't matter what you do because we're demonstrating simultaneous branching, not structured text. So I'll put this in the edit mode, which it is right now, and I think I will make this 5. So I turn on 4, turn off 5, and here I turn off 4 and turn on 5. That should do it. Now I look over and I see that output 4 is on and output 5 is off. Notice that this did not bump us back to the start step because it was simply an edit of the tags and the actions. We did not actually change the structure of the sequential function chart. You remember in past lab projects, if we were actually editing the structure of the SFC, we would have got that little pop-up yellow message that warned us that it would bump us back to the first step. Let me push input 3. Now we have on 5 and 4 is off. So if we press input 4, we go back to start, press input 0, we're in step 1. We could take out the reset action that resets action 1. No reason to, because this is just sequential function charts. There is much more to sequential function charts. We have barely touched the tip of the iceberg. I decided to go back to the selection diverge and do some experimentation. It occurred to me that I could add one more little caveat to our selection diverge here. So I'm going to put this in the edit mode, and I'm going to watch this button up here, which is extend branch. So I'm going to click on this, I'm going to extend this. See, that adds another transition. Then I'm going to, I extended the branch, it gives me another transition. So I'm going to call this transition 400. A defined tag, so we'll make it a new tag. And then of course we need a transition tag. Now here's where it got a little tricky. I went through and started selecting things to see how I could converge the elements, but I only have one element. What I discovered was that you drag the line down to one of these two. Looks like either one of them will work. You let go and now you have a transition that bypasses. So let's finalize this and see if it likes it. Now see, here we get the message because we actually changed the structure. So it's going to bump us back to the start. And that disappears on its own when there's no errors. So now let's transition into step 100. If we use transition 400, watch. it went right back to the start. We bypassed step 200 and step 300. So this is a little caveat that occurred to me while I was recording the lab. What if you don't want to execute either one of those? You have a bypass. Well, I think that about covers everything we want to do in sequential function charts. I realize this wasn't probably the best video I've ever produced. I don't use sequential function charts very much. I would be the first person to admit that. However, I wanted to give you enough just to get you started. If you like sequential function charts, and by the way, I like them much better than I used to when I first started playing with them, I wasn't real excited about them. I still don't see a real good application within the venue that I work in, the type of machines and processes that I work in. I don't see a real application for sequential function charts. However, the arena that I do engineering in is very narrow compared to everything out there. Before we completely conclude this section on sequential function charts, at the end of the manual I threw in a challenge to write some code that sequenced 5 lights. And here is that challenge explaining just one possible solution of many, many solutions. We are online now with this and running. This is one solution. Unfortunately, the update time of the system, meaning the laptop, and we are using 38.4 baud rate through RS-232, does not allow us to see anything stepping through the sequence, even if we go to the watch. So I'm going to go to View, and this is really slow because of the speed. So we turn on the watch, which you can't see. I'm going to have to drag it up. So you can see the bits here. You do see them changing once in a while, but you're not seeing them sequencing in a quarter of a second apart. So what we're going to do is we're going to increase the time delay to slow down the sequencing to see if we can catch it on the screen. So I'm going to close the watch. I'm going to go into the edit mode. Now I'm in the edit mode. I'm going to go to the preset for each of the time delays and set it to 1 second. There are other ways we could do this. We could add some actions in earlier steps. For instance, we could have a selection branch here. We could use 2 switches, one to run low speed and one to run high speed. And so we would have, instead of having just step 100, we would have 2 steps above here. One step set the time base at a quarter of a second, and the other one sets it at 1 second. Let's finish this. Okay, now all of them are set to 1 second or 1,000 milliseconds. We'll finalize all edits. Remember, we're doing this on the fly. I can see the lights flashing right now. They're already using the 1 second time base. You can't see that yet because we were still downloading. But now, if you look up there, you'll see them sequencing through. Yep, you didn't see 500 that time. We're still too slow to see all of them sequencing. So let's go back to the edit mode and bump them up to 1.5 seconds. Now let's watch. There's 500, step 100, step 200, 300, 400, 500. And if we bring up the watch, so we go to View, you can't see it because it's out of your viewing area, but I'm clicking on View and then clicking on Watch, and up it comes. So you can see the bits now sequencing in order. Now if we were using Ethernet instead of RS-232, if we were using 100 meg, I mean seriously, 100 meg versus 38.4K. However, like I said, I've got my Ethernet interface card that my neck tied up doing something else. I don't want to interrupt it. This will be good encouragement not to use RS-232 unless you have to. I typically consider RS-232 the back door into the Logix engine. And it's good to know how to use the RS-232 port, because if you're having trouble configuring your Ethernet, in other words, it's configured with a fixed IP, and you don't have a sniffer or any way to determine what the IP is, then you need to go in through RS-232, look to see what the IP is, so you can set your external IPs or change it to match the network that you're putting the controller on. So let me close this. There you go. That's one solution right there. So you can see this is our switch that we're controlling whether or not it's cycling. And by the way, because with each successive step it comes back to start, if you turn off that switch, it's going to stop with the outputs in the position they were in when it cycled back to start. So in the first step it says if local 10 or O data, output data, and that's the whole 16 bits. If it equals 0, because you have to get this thing started. I don't know what you did for yours, but I says, okay, if none of the bits are set, or if bit 4 is set, meaning that it's gone all the way through the sequence, then set bit 0 equal to 1 and set bit 4 equal to 0. And of course, if bit 4 was already 0, setting it to 0 isn't going to hurt anything. So step 100 gets our sequence started, so to speak, or reset. So I don't see any way that this could get hung up. You know, I've not spent a whole bunch of time looking at this. The only purpose for doing this little piece of Space Cadet code is an exercise in understanding how sequential function charts work. Now, we could come up with all kinds of other little challenges. Maybe we'll add some later on. Thanks for playing. Well, I just couldn't help myself. I had to throw in one more solution. This is probably the simplest solution. The other one was binary. This one is integer. So we've simplified step 100, the action. If the output card data equals 0, or if bit 4 is on, then set the whole card to 1. Not just set the first bit to 1, set the whole card to 1. And then we still have the individual bits doing the transition, but in the action, instead of turning on one bit and turning off the rest of them, we're setting the whole integer to one value. So here it's set to 1, which is the first light, and then 2, 4, 8, 16. If you wanted to extrapolate this to more outputs in sequence, you would use the extend branch, and you could repeat these little 3 pieces here, and the next one would be 32, then 64, then 128, then 256, and so on. I just thought I would throw in one more solution here. This one is actually the easiest one to type in, but it's not as apparent as the other one. Thank you for watching the lab wrap-up lecture discussion on languages. This was the last section of the sequential function charts.